Hello everyone, my name is Rory Shraga and I'm an assistant professor at WPI, and today I'm going to present a work that was done during my postdoc at Northeastern University in collaboration with Professor René Miller, and I'm going to present to you a work that talks about explaining dataset changes for semantic data versioning with explain-the-V. So let's assume that we have a dataset version here that talks about movies that was created by user A. This version has a lot of other versions out there in the world. Here, for example, is another version of this dataset that was created by user B. Here, specifically, we assume that user B used the version that was used by user A to derive this version. And specifically, our goal in this work is to explain the changes that was done by user B. Specifically here in this example, we see that one row was removed, here M4, and 4 new attributes were added, A5 through A8. Let's look at our proposed solution. Here we see version A that we saw before. Row 4, or M4, was removed because it contained a noun value, a very common thing to do as a data scientist. A5 was created by extracting the certificate numbers, or IDs, from A1. A6 was generated using a numeric transformation that moved from runtime in minutes to runtime in hours in A6. A7 was created by regenerating the rating system that was introduced in A3. And finally, A8 attribute was added to count the number of characters that appeared in A1. So our goal in this work is to find an automated way to generate this explanation. Just as an highlight, in the literature, only the transformation that I mentioned for A5 is covered. Before we move to our problem definition, we will look at related work. First, data versioning was explored mainly throughout storage, management, and discovery perspective. Data change, difference, and integration was explored quite broadly and relate to our work in the sense that our work relies on the changes that happen, and we are trying to explain not only what happened, but how it happened in practice. And finally, data transformation by example largely looks at transformations that occurred in the data and tries to recover them, which is the main technique that we use trying to explain the changes in our work. Our problem definition looks at 3 main components. The first is the origin, the second is the goal, and finally, the transformation that tries to explain the goal using the origin. Let's look at an example here with A5. Here, A5 was explained using A1 as an origin, and a function that uses extract to extract a certain value from A1 using a specific pattern. So, in our terms, A5 is the goal, A1 is the origin, and extract this specific pattern from A1 is the transformation. So how do we explain change? Specifically, we look at 3 main data types: numeric, categorical, and textual. And we make a few important assumptions. First, we only look at internal changes, so no integration was introduced here. The changes are known, so we know which attributes and tuples match between 2 versions that we look at. And finally, we look at only data-driven changes, so we assume that the metadata is not introduced here. Here we saw in our example that the names were A1, A2, and A3, and so on. So we didn't have the semantic to work with when trying to explain changes. Let's look at the types of explanations that we are generating. First, we look at numeric explanations. Here, both the goal and the origin are numeric. So the goal is the attribute that we are trying to explain, or the change that we are trying to explain. And the origin is the origin of this change. Here we assume both of them are numeric. Specifically, we position that as a regression problem. We add some regularization to these regressors, and we base our solution based on linear regression because we want to introduce explainability to the solution. Our work also introduces extensions such as polynomial regressions and some math operations that try to cover more ground of transformation that exists out there. The second type of transformation that I'm going to cover in this talk is categorical explanations. Specifically, the goal here is categorical, and the origin is normally a numeric value. Here, we cast the problem as a classification problem, and again, to enhance explainability, we build on top of decision trees. So far, we saw mainly examples that use attributes as the changed components. Here, I want to show you an example that looks at tuple changes. Here, for example, we see that 3 different rows were removed, and we're trying to explain what happened here. Since we cast this problem as a categorical explanation, and we're trying to recover the predicate that is used to recover this change. So what type of changes are we looking at? Let's look at version A here. So we look at vertical changes, the type of changes that deals with columns, and we look at additional ones, so basically adding new attributes, and removal ones that basically look at removing attributes. We also look at horizontal changes, specifically added tuples and removed tuples. Note that changes can be more than one type. For example, if we look at this version here, that is very common in the data that we work with, it introduces every type of possible change that we consider, which makes everything far more challenging to the method. When we look at vertical changes, again, when we deal with attributes, we also look at one additional component which we refer to as find the origin. Specifically, when we look at these type of changes, there has been some sort of origin to these changes that occurred there. And specifically, as a byproduct, a functional dependency was created because, you know, when you change a value, you do that using a transformation that is consistent throughout the change in this column. So we use this functional dependency discovery trying to recover the origin of this data set. As I mentioned before, we also cover other types of changes, and more details are in the paper, and I'm happy to answer more questions offline. When we look at evaluating the explanations that are generated, we look at a few main components. And specifically, the main question that we ask ourselves is, how do we compare among possible explanations? So let's look back at our example, and here is a new example that introduces a few additional columns to our data. And specifically here, we have A11 that basically looks at attributes or movies that have a rating over 8. Right, so let's look here. 9.2 was assigned with 1, 8 was assigned with 0, 7.6 was assigned with 0, and so on. But then there are some questions that we can ask here. For example, can we change the root to look at A2, for example? Here, we see that maybe it's incidental, but specifically we can see that even if we look at A2 over 150, we still get an explanation that is still true. Maybe we can change something else. Can we say that A3 is larger than 7.5? So here the answer is a bit easier, right? Because we can see that, for example, we will miss M3 here, which instead of being a 0 value, as it's supposed to be, it will be transformed into a 1 value. Taking advantage of that, we want explanations to be valid. So basically, when we apply this transformation, we get the new column that we wanted, as we mentioned before. So the second example that I showed here is not valid, while the first one is valid. We want our explanations to be generalizable. So specifically, we can assume that if the user, the original user that created the change, looked at movies over 8, the first explanation that I gave here as an alternative would not hold in most cases, because it's not very common, or it's not always the case, that movies that run over 150 also have a rating over 8. And finally, and one important ingredient, is the explainability of such solutions. So we want these explanations to be explainable, and we introduced two new measures for explainability whose details are given in the paper. I'll be happy to talk more offline about that. So when we choose an explanation, what were we looking at? First, we want our explanations to be valid. So basically to recover the same attribute or the same row or whatever change that we were looking at that we saw before. We also want them to be generalizable, but we cannot tell for sure unless we have additional data that we can use. And finally, we want the explanations to be explainable. So for a user to be able to understand what is going on with the explanations. And specifically what we do here is we first find the one with the highest validity in the set. So basically, an explanation that imitates and generates the change that we have. Second of all, if we have multiple explanations with the same value, what we are trying to do is to find the one that is most explainable, because we want benefit to the output in the output for the user. Some comments. First of all, we introduce an early stop condition. And this condition is based on some threshold that is introduced for validity and explainability. For example, we can say we're happy with a 95% valid solution. So basically only 95% of the values are transformed correctly. And we benefit from that, in runtime. And in practice, when we introduced a 0.95 or 95% validity threshold in our experiments, we saw that 70% out of the cases were actually terminated early, which is very beneficial in runtime, but also generated a nice case of good explanations for the user. Let's look at some experiments before we wrap things up. We built on top of one existing data pipeline synthesis called AutoPipeline that exists in the literature, which is very similar to our approach in a lot of manners. But we also created a new semantic version benchmark that is available online and is shared here that introduces different topics of versions and in general introduces hundreds of dataset versions and annotated changes that we can use for evaluation in our experiments. So as I mentioned before, we have 5 different topics here: IMDb, NBA, one Iris and Titanic, and one existing benchmark that is called AutoPipeline. We have several baselines that we considered. We can see here that our method outperforms most of them, or all of them basically. And one important note here is that it's not coincidental that these names of these data sets are familiar to you. Because what we try to do in generating these benchmarks is to build on top of very common data sets in the data mining community, in the machine learning community. Because these are common data sets that have a lot of versions out there. So we try to do that in a very real world like fashion. This data set and the results are open source and available online. So what did we learn in this work? First, numeric data is everywhere, even in data lakes. Research in the area so far has overlooked the numeric values in data lakes. In this work, we saw that even fairly simple machine learning solutions can be beneficial to make sense out of these data types and can be used to better understand what type of data that exists out there in data lakes. Second, documentation in data science is very important. We saw in this work that some of these documentation components can be recovered using transformation by example techniques. However, not every type of change is possible to recover this way. And finally, externality is actually hard to explain. So this work does an effort trying to generate explainability measures in order to overcome user studies. And we believe that these measures can be very beneficial even if a user study is actually introduced. So thank you so much for listening, and I'm available here if you have any additional questions. Unfortunately, I won't be here at VLDB this year, but I'm happy to take any question offline. Thank you again for listening.